All right, we're back. Okay, so the amount of material to cover here is too much, and I'll just try to start you on this. And if you're really interested, you should also take Dr. Klipinstein's class. And then if you're really interested, you should really take a whole class in this. But if you want to read about it, I think this article, it's a long time ago, 1996, but this is a really good article about the status of the transition state theory, about how what the theory is, and what things you can compute well as of that time. And then what's happened primarily after that is that for normal reactions over barriers, it's just been the precision is improved, and primarily because of improvements in the quantum chemistry, and a little bit in improvements of the treating of the floppy motions for molecules and transition states that have floppy motions. This paper, RKM theory, and especially this paper, master equation methods in gas phase chemical kinetics, this is a very key paper to read, future article in JPhys Chem about how to do pressure-dependent rate coefficient calculation. So if you have a reaction where the collisional energy transfer is contributing significantly to the rate, so it's either rate controlling or not insignificant, that there's like a hindrance to the reaction or something's happening because of the slow collisional energy transfer. You can't make the Boltzmann approximation. So this theory up here is mostly all about if you make the Boltzmann approximation. This is saying if the Boltzmann approximation doesn't work, it means that the system is not perfectly thermalized at all times. How do you do it? This gives equations about how you do it. And so if you're in those kind of reactions, that's very important to know. And it turns out there's a lot of simplifications in that paper. They figure out a lot of things. And then these things here. This one, for example, the association kinetics of two alkyl radicals. This is all about how to predict reactions with no barriers. So the formula I'm going to show you is really only for cases where there's a barrier. So this gets back to this issue about how can I define what a species is. And if you're a species, you have to be able to have a dividing surface. And the normal way to define the species is as the valley, and the dividing surface as the mountains, separating the valleys. And if there are no mountains, you're out in the Great Plains, you know, what the heck is the barrier between Kansas and eastern Colorado? You know, unless there was a sign there that says, "Welcome to Colorado," you'd have no idea, right? All right? And so it's the same thing in the molecules. Unless you need something, there's no signs there to tell the molecules that now you're this species and before you were that species. And so how to even define what you mean by the reaction is problematic. And then the methods to calculate it are also different. And Dr. Klipinstein invented most of the methods that are good. And this paper with him as the first author, this is a really important paper for understanding that stuff. Yeah, I think that's about it. So, and you know, as a student getting started in the field, the review articles are great because the person writing the article is trying to give you the full story. Whereas most of the articles in a journal are not the full story. They're a specific little tiny story about some specific little thing, right? And they're trying to get that little specific part exactly right, and that's it. But they're not trying to get the whole context of the whole world. But these review articles are trying to give you the whole context. So I think you might find them pretty good to read. All right, so just what we talked about with the thermochemistry, in computing rates, we always start with the Born-Oppenheimer approximation, which means that we take the original Schrodinger equation, which treats all the nuclei, the atoms, and the electrons on the same basis, and we say, you know what, the atoms are pretty heavy. They're sort of almost classical. So let's just, and the electrons are super light, and they're definitely quantum mechanical. So let's first just freeze the atoms so they're not moving, get rid of the terms that have to do with the motion of the atoms, and only leave the terms that have to do with the motion of the electrons, and solve the electron motion as if the atoms aren't moving. So I'm a middle-aged man. I would take my kids to the boardwalk. How many of you guys have been to the boardwalk? Oh, this is not going to work. Okay, for your cultural education, since you're in New Jersey, what people in New Jersey do in the summer is they go to the beach, and at the beach, they've built these walks out of boards, literally. called the boardwalk. If you play Monopoly, the boardwalk is the key square to get Monopoly. Anyway, what they did was they built a pier, put sticks into the sand, and lifted up this elevated walkway. And in the evening, you can walk along, and you can look out on one side, and you see the ocean. It's very pretty. The moonlight on the ocean is very nice. And on the other side, they built every kind of glitzy, neon, tourist trap thing you ever saw in your life, all jammed together on that side. And so I would buy caramel popcorn there, a big giant, these big buckets for millions of dollars. And I've spent all my money to buy this big thing of candy popcorn. Tastes delicious. And I'd walk along, and I'd have all my kids and my nephews and nieces. I would all follow me because they wanted to keep reaching in and grabbing the candy popcorn. And I'm slow, I'm old, I'm walking along, I'm tired, I'm taking care of all these kids, right? And the kids, of course, they're super excited. They're eating all the sugar, they're running around. It's so exciting to see all these tourist traps and amusement rides and ways they can spend money. They're so happy. So they're flying around. You see the seagulls. They throw rocks at the seagulls. They throw sand at their brother's face. Right? They're doing everything. And they're like a cloud of electrons. I'm like the stable nucleus. I weigh as much as all 6 of them all together. Right? I'm walking along. And they follow me because they are attracted to me because I have the candy popcorn. Okay? So that's the way it is in the molecule. The atoms are big, heavy, fat guys. They slowly move along, but they have a big attractive force. They have a lot of protons. All the electrons want to stick to them. And so wherever the atoms move, there's like a cloud of electrons around them. Okay, so that's the idea of the nuclei. And from the point of view of modeling me in the boardwalk, you can basically take me as stationary, and you can just watch the kids move around, because it's happening at a much faster time scale compared to my slow motion down the boardwalk. Okay. Yeah. And my key thing is I just have to make sure I make it back to the car before all the popcorn's gone, because that way I'll be sure that all the kids make it to the car. Got to go home. Otherwise, I might lose a kid on the boardwalk, and that would be bad. All right. All right. So the nuclei are basically are stationary, and the electrons zip around. That's what the Born-Oppenheimer approximation is. By the way, Oppenheimer was the guy who was in charge of the Manhattan Project. I didn't know this. Anyway, he invented this when he was like a visiting graduate student or postdoc in Germany in Max Born's lab. So the electrons are very quantum mechanical. They're like waves, and they also satisfy this Pauli exclusion principle. They have this Schrodinger wave equation, and the atoms mostly act like classical particles, and they just feel the time average force basically exerted by the electrons flying around them. And so the way to solve it is you solve the electron motion problem first, assume the nuclei are fixed, and you get the potential field V of R. We talked about this a few times. And you can use programs like Gaussian or MolPro to compute this V of R. And this turns out it's really hard. And so you can use these high accuracy methods, things like CCSD parentheses T and the F12 and all this kind of stuff, if you really want to get really good numbers. But if you don't have such a big computer budget or you're impatient, you can't wait to run the long calculations, you can just run DFT, and in an afternoon you can calculate everything about your molecule, of course inaccurately, but fast. And so that's what people usually do. They do this first, and later when they really care about something, they go back and try to do this really high fancy stuff to get a better solution. And then you get whatever V of R, whatever method you used, then you're going to use it to try to calculate the rate. So remember back in the very first lecture, I think we talked about how you compute a rate coefficient with classically. I mean, first of all, by counting cars crossing the toll plaza. That's the first picture. And then you can say, well, now in atoms, they're not like cars. They're actually follow a Boltzmann distribution, and they're all wiggling around. And so we can do the classical analysis for if you have a perfect Boltzmann thermalized system. And the key thing is defining the dividing surface, S of Q. And when S of Q is equal to 0, that's your boundary between your reactants and your products. And we just can sample from the reactant phase space and see the probability of the trajectory moving across. But it's actually simpler, but just stand at the toll plaza and wait till the cars come to you. So don't worry about simulating how they move around. Internally, just wait till they get to the boundary and then measure what happens at the boundary. And the fraction that changes from reactants to products per second, that turns out to be the rate coefficient, basically. And so here's a picture. So we have a contour, And if you start in this valley, you have some trajectories, and they can wiggle around. A lot of them just stay inside the valley, but some of them can wind their way up and find their way over the mountain pass, which here is probably around here somewhere, and then down over the mountain pass into a region over here. And sometimes you have trajectories that might come in and turn around, and some of them come in and find their wells all the way down. And these are the formulas for the K, the classical expression for it. And you can have, I showed you it was all canonical, which means I assumed perfect Boltzmann distribution. You can also have microcanonical, where you're assuming that the energy is conserved. And for those cases where you're limited by the collisional energy transfer, where that's the slow step, then this is the right way to think about it, because you're like basically locked at a certain energy, and there's no way to get rid of the energy. And so you stay at a certain energy, and then you should use a delta function in energy. And in some cases, if you're in a high vacuum, you have like no collisions at all. The poor molecule's floating around there all by itself for a long time, like in interstellar space. You have a molecule out there. It can't do any collisions, so it can't even change its angular momentum. It just keeps spinning at exactly the same angular momentum all the time. It has the same energy all the time. And then you should do microcanonical with J resolve. So the J is a constant of the motion, and E is also a constant of the motion. And so these are different expressions for the probability of having a certain position and a certain momentum, depending on what physical situation you are. Boltzmann, E conserved, E J conserved. And then this thing is like your probability that you're at the boundary, and this is your rate across the boundary, your flux. And this just counts if the trajectory is going from reactant to product or not. Then you'll say it's 1. If it's not, then it doesn't contribute. So that's the classical trajectory expression. And you can rewrite them, and as we showed, with a certain special case where you draw the dividing surface at a special place. The best place to draw it is actually at the saddle point. So you find a saddle point in the mountain. That's the mountain pass. And when you get to a mountain pass, you're climbing up the pass, and you say, hey, I'm at the top. I can see down the other side. And then you start going down, right? And so right at the top is the place to put your dividing surface. And you say that I am moving on the pathway that goes, the minimum energy pathway from the reactants to the products. And I stop there. I'm facing in the direction of the minimum energy pathway, and the boundary surface is orthogonal to me. And so if I'm on this side, I'm in product space. If I'm on this side, I'm in reactant space. And here's my dividing surface. And if I draw a plane, a hyperplane, that's perpendicular to that direction of motion that's along the minimum energy path, that's a clear definition of a dividing surface. And it gives you really simple algebra, because it's a plane. It's Cartesian. You don't get any funny factors with Euler angles and goofball stuff. Everything's really simple, and you get this really simple expression with that expression. And the simple expression is that this energy is the lowest, the peak value of the potential energy along the minimum energy pathway from the reactant to the products. So the highest energy that you have to get over, you find the lowest energy pathway to get there, and the peak along that path is this E double dagger thing. And this is actually the difference between that and the energy you were at the bottom of the reactant valley. So it's basically the altitude gain that you have to achieve in order to get out of my valley. And the Q for the reactant is just a normal partition function that we've talked about a lot. It's just basically the Boltzmann average over things that are in the valley. And the Q dagger thing in the numerator, this is Boltzmann average, but over things which are sitting at the boundary. Only count Qs that are on the boundary, at the toll plaza. And then, and we've already computed the P integral, so don't include the P integral in the direction orthogonal to the boundary. That's already been computed, and that's where we got this KT here, the KT over H factor from. And so that's the expression. And we saw that already one time before. And this is a picture of what it looks like. So you have your reactance situation and your products and your what we call the transition state, which is the state on the boundary at the minimum energy, at the saddle point. And now we're going to say, well, we were talking all classically until now, but now we're going to realize that actually the systems are not classical because the molecules have 0-point energy. So we have to consider the fact that this energy of the molecule, the minimum energy it can take, is not the energy at the bottom of the well, but it has a little bit of 0-point energy on top. And we have to consider that. And the same, the reactants have a little bit of energy. And the difference between the 0-point energy here and the 0-point energy here is what we call like delta U or delta H at 0 Kelvin. Okay, that's the minimum energy difference between the reactants and the products that you can physically achieve, including the effects of quantum mechanics, which say that there's 0-point energy. And that's what you would measure if you measure the energy difference at 0 Kelvin. And then we can do the same kind of difference between the reactants and the transition state. And the transition state will also have 0-point energy in the modes orthogonal to the reaction. So in addition to there's a certain bond that's breaking and making, it's making the reaction. You have a lot of other vibrations in the molecule. They are just basically the same as they are in a stable molecule. They still have 0-point energy, just like before. And so there's a 0-point energy associated with them. And these 0-point energy values are usually similar to each other, but not the same. They might differ by a couple kcals per mole, kind of typically. And the difference in the energy between this 0-point and that 0-point is what we call delta E0. And that's the 0-point corrected difference in the energy. So if I was doing classical mechanics, I would be very concerned about the energy difference between the bottom of the valley and the saddle point, or the altitude difference there. That was the energy that I have to go up. But now I'm correcting it for the 0-point. I'll get a slightly different number because I'm going from the 0-point of the valley to the 0-point of the transition state. All right. By the way, the E0 in the forward direction and the E0 in the reverse direction are related by the delta H. Do you see that? That this guy adds up. So if I know the 0-point corrected barrier in the forward direction, and I know the enthalpy change from the two, from thermo, I then also know the barrier in the reverse direction. And so they satisfy inequality here. So this is another example of how you need to know the thermo to help you figure out the reverse rates. All right. Now, the formula that I showed you so far was kind of implicitly for unimolecular reactions. It didn't have any concentration factors in it at all. It just gave you a number that was in units of per second. But in reality, we often want to do bimolecular reactions. And so we want a reaction with units of volume per time, because we're going to multiply it times two concentration factors. It's going to be K times concentration of A times concentration of B. And for the units to all work out, I need it to be in units of volume per time. And the correct way to do it is to divide the Q's all by the volume. If you remember, in the ideal gas expression, particle in a box, the Q's are all proportional to the volume of the system. And so what this is saying is just forget those volume factors. Remove them all, and now have all your Q's will have units of per volume. These Q over V factors, all units of per volume. And if you put those in, then you get everything right. So that's what you should do. And here's the energy difference, 0-point corrected. Here's the Q's over V. This is our KT over H. And here's some extra factors in the beginning. I'll tell you about these guys. So one factor in the beginning here is symmetry factors. So we mentioned before, when you do the rotational partition function, you have to account for the indistinguishability of atoms. And so if you have a molecule like ammonia, there's 3 hydrogen atoms. You can rotate around 1/3 of the way, and it gets to an indistinguishable configuration. You can't tell it apart. So you have to divide like somewhere by a factor of 3, somewhere when you're trying to compute the Q correctly to include the quantum mechanics. In quantum world, they're indistinguishable. In classical mechanics world, usually we say they are distinguishable. You would call it atom 1, atom 2, atom 3, and you think they were different. But in quantum mechanics, they really are indistinguishable particles, and you have to account for that. So you get these extra factors. That's what these sigmas are. And the reactants will have sigmas, and the transition state also could be symmetrical, and it could have some sigmas too. And then there's an extra factor. This is super confusing. Some reactions, when you get to the reaction state, are chiral. That means that there's a mirror image transition state that is distinguishable, that is different. If you have a weird reaction like that where that happens, then you actually get an extra factor of 2 in the rate, because it could happen either way. And so let's give an example. So if I had the reaction of iodine atom adding to CFCl H. So let's draw this. This is C with an F atom, a chlorine atom, an H atom. This is a radical. And these two guys could recombine, and they'll make something as CFClHI. I don't know how you write that exactly. Okay, which is like a tetrahedral molecule with a carbon atom in the center and a fluorine, a chlorine, and a hydrogen and iodine on them. This guy is chiral because there's 2 different forms of this that are mirror images of each other that you cannot rotate them and put them on top of each other. So it's a chiral carbon atom. The saddle point, as this I approaches, it sort of, does it approach from the top or from the other side, from in the board? They'll actually make 2 transition states which are different. They're different chirality. So you have to be aware of that effect, and then you get a factor of 2. That's what this M is. And then in this case, it's kind of clear because you're making a chiral product. Sometimes this happens in the case where both the products and the reactants, none of them are chiral. Only the transition state is chiral. You get this extra mysterious factor of 2 appears out of nowhere. So that's just to be aware of. And then this kappa factor, is a fudge factor that's correcting for tunneling. So another really peculiar thing about quantum mechanics is that you don't actually have to go over the barrier. You can sneak through the barrier somehow. And that's because the atoms are not classical. Their positions are like a wave function. And the wave functions have tails all the way up to infinity. And there's a little bit of probability that you think the atom is here, but there's a little bit of probability it's actually over there. It's a very small probability that it's all the way over there, but there's still a little bit of probability. And that probability could even be on the other side of a barrier. So this guy, 99.999% of the time you see it in this valley, but a certain percent of the time it's suddenly in the other valley. And that tunneling effect means that the effective rate at which how fast you see things in the other valley is different than what you would have gotten in classical mechanics. And that's what this kappa factor is for. As we talked about before, the key factor, of course, is the Arrhenius factor, right? All these guys are linear, but the Arrhenius factor is exponential. So this is like the big kahuna, right? This is like dominating what's going on, and all the other stuff is like fine decoration after you bought the house, This is the mortgage, right? This is the decorating cost. So you got to get the mortgage right. You got to get the big number right before you worry about the rest. And it's all because of this Boltzmann factor, just as we talked about before. And little tiny changes in the temperature make a huge effect, and also little tiny errors in this delta E0. If you make a small error in this number, you're way off. Whereas you make small errors in these guys, you're just off by whatever. You're off by 10% here, you're off by 10%. You're off by 10% here, it might be off by a factor of 1,000,000. So it's a big difference. All right, so this is all about the transition. Now, we talked before about dividing surfaces, how important they are. I gave you the formula for the most simple way of defining the dividing surface, but actually, you are free. You own these molecules. You can call them whatever you want. Right? I don't know if you know the book of Genesis. God told the humans that they're allowed to name everything. Right? So we can name the molecules what we want. I don't know why we name them iodoalkane or whatever crazy names we give them. The UPAC names, it seems like it wasn't really that well thought out. But anyway, human committees got together and decided how to name the stuff, and we can name them what we want. We can define what our species are, and we can define what our dividing surfaces are, and whatever we want. And you can make a family of dividing surfaces, and we showed before, like in trying to figure out the flux of cars from New Jersey to Manhattan, we showed the case of drawing different dividing surfaces around the George Washington Bridge toll plaza, and actually, depending on where you drove the dividing surface, you can actually get different numbers. Same thing happens in the molecules, and it can be much more subtle and not so easy to see what's going on. And so the way that Dr. Klippenstein suggested that we should do it is actually define a family of dividing surfaces and then scan over the whole family of possible dividing surfaces. And his rule of thumb is whichever dividing surface gives you the smallest rate, that's the one you want. The one that minimizes it, because it's going to, as I showed in that case, in the New Jersey case, if you drew the dividing surface poorly, you might count the same car twice. And so this is a way to try to just count them once. And typically it's to choose the one that's the minimum. And so then this gives you like a variational principle about how to define dividing surfaces. And so he has software that will help you try to do that. All right, so transition state theory is not really exact. Part of it's because we can't really define the dividing surfaces perfectly, and then we usually make a lot of approximations along the way here. We made the Born-Oppenheimer approximation. We make this approximation of using Cartesian planar dividing surfaces when really they're curved. There's a lot of other approximations we make. We use the rigid rotor harmonic oscillator to compute the Qs, even though they're not really harmonic oscillators. In fact, they're not even really rigid. So there's a lot of things that we've done that are inaccurate in this. But why do we do it? So the key thing is that the chemical models for combustion, we need thousands of rate coefficients, a very large number of rate coefficients. We don't have the resources to try to get perfect numbers for every single number in these models. So we have to accept that we're going to have some errors, and therefore it's not just how accurate something is, but accuracy like per time, or accuracy per amount of effort is an important thing. And so transition state theory gives you pretty high accuracy per amount of effort. Experiments are often way too time consuming. It's really hard, and unless we really care about a reaction, we're not going to do the experiment. And often you can't do the experiments at the T and P of interest anyway. So at some point you're going to have to do a calculation to help you extrapolate to a different temperature and pressure where you can't measure it. Theory, you can do a lot with empirical models, correlations, and extrapolations from known information. And in fact, that's what most of the kinetic models that you guys will be using, a lot of the numbers are derived that way. But it's risky. You're extrapolating with no data, no calculation even. All you're just saying is, I think this reaction is a lot like that reaction. Let's use the same numbers. That's all you do, right? And so that's a risky thing to do. And if you want ballpark right, it's usually within 2 orders of magnitude, 3 orders of magnitude, you'll be right. But if you want precision better than 2 orders of magnitude, then maybe not. And you really should look into it. And so this is, it's good as your very first rough guess, but if you want to actually have a number, you should do something better. You can do classical trajectories, and you'll see some people do this a lot. It's called molecular dynamics. You might have seen papers like this where they have atoms wiggling around, and you can see them atoms wiggling around. Occasionally they break apart and react. It's kind of cool. It makes great cartoons, videos. It's really not a very good way to go because you cannot afford to run those calculations and actually sample the reactions. And the reason why is that the reactions are rare events, right? Only the tiny little bit of the molecules out here are going to react. All the rest of the molecules are not reacting. They're just wiggling around. And if you try to do the simulation that's accurate, and you do a sample, finite size sample, and you look in your simulation, all you should see is that almost all the molecules are just wiggling around. And you spend all your computer time computing them just wiggling around. And occasionally, if you're lucky, one of them breaks or does a reaction. But you don't get good counting statistics. You don't get enough events. So just doing molecular dynamics is a foolish way to try to compute the rates. Doesn't mean that people don't do it. Why am I doing this? A lot of people will do it anyway, but it's foolish. And you'll see that the best people can do these days is typically like simulate for a nanosecond. So it's only a valid way to go if you have reactions where you expect a lot of events to happen in a nanosecond. But usually we don't care about reactions that are that fast, right? Because from our scale, if it's going to happen in less than a nanosecond, then it already happened. And I don't even bother to include it as a rate process, right? It just assume it's done. So this is really not a very good thing. Also, a lot of things will do this with classical mechanics. They don't include any quantum effects at all. And particularly, they don't include the 0-point energy. And for reactions, the 0-point energy is a couple of kcals in the barrier height, which means a couple of kcals in the activation energy. A couple of kcals is a lot. So you're like immediately accepting quite a big error if you don't include the 0-point energy effect. So if you ever see anybody who writes papers like this, you should tell them, write something else. Do something else with your time. There are ways to try to patch this where you can do methods that include the quantum mechanical effects. And one of the methods I've done papers on is called RPMD. And we have software you can download for free if you want to do it. And you can do it, and you get the quantum mechanical effects. And I would say you get slightly better rates than you would get by doing the transition state theory, by doing that, but at a lot more computer cost. So then you have to think of what you want to do. And again, it's only good if you can cleverly bias the sampling and stuff to try to increase the probability of seeing the reactions you want. You could solve the real quantum dynamics problem. So instead of making the transition state approximation, you could solve what are called the scattering equations of quantum mechanics of what happens when two things bump into each other and what's the probability that they react. But this turns out that if you have more than 4 atoms, you're not going to be able to afford it. There's one example in the literature, somebody did one with 5 atoms. That's like the heroic calculation. So if you have any systems bigger than 5 atoms, this is really not a viable option. So given that all your alternatives don't really work that well, this is what you want to do, is transition state theory. And so that's why we're teaching you that. All right, so we started out with Born-Oppenheimer where we're sort of assuming that the atoms are classical and the electrons are quantum mechanical. We solved the V of R that way. But then we just say, well, you know, in reality, the atoms are quantum mechanical. They tunnel. They have 0-point energy. We have to worry about quantum mechanics a little bit. And sometime, I think maybe late 1990s, a guy named William Miller, who's a professor at Berkeley, figured out that actually there's a quantum mechanical version of transition state theory. That you can actually start as if you're doing classical mechanics, transition state theory, get the operators and stuff like you would, and convert all that classical expression exactly into quantum mechanical language and write down what the quantum mechanical operator that corresponds to the transition state theory is. He wrote down the exact version, which gives the exact quantum mechanical operator for a rate. It's a lot better than doing the full quantum scattering, but still it's really expensive. And this is actually the method that was used for the 5-atom system. A guy named Manthi did it. But then you take his exact quantum mechanical formulation and make some little tiny approximations on it. And you get something that looks a heck of a lot like the transition state theory that we all do already. And so there's like a much, at the time the transition state theory was proposed, the connection of that to quantum mechanics was not clear at all. That was back in the 1930s. But now there's a very rigorous thing, and you can say exactly what approximations you're making if you're using the transition state theory expression instead of doing quantum mechanics. Yeah, here we go. So if you're willing to do it, you get this nice, cheap, and convenient recipe for computing the rates. So here's the recipe. So everywhere you saw a Q in the formula, replace it with the rigid rotor harmonic oscillator formula that we use for thermo. Always use Q trans of V over N instead of using the dimensionless Q trans. Correct the barrier height in the classical expression with a 0-point energy difference. If you have the mirror transition states, add your factor of 2, put in your symmetry numbers, and then the tunneling correction. I don't know if I'll talk about that very much, but there's several ways you can do that. And then what you have to do is find the saddle point geometry. So you have to, typically you would do a density functional theory calculation to find a saddle point. You say that this is my transition state geometry, and then you would do a second derivative calculation of the potential expanded around that saddle point. So the second derivative is d squared v dr. At the saddle point. You also do one for the reactants as well. And then you just go ahead and plug those numbers into the transition state theory and stat mech formulas. And you probably have a pretty good estimate, except your weakness most likely will be your energy. So as I said, the big issue is the energy. And the key here is that there's the big giant barrier height energy, the classical barrier, and then the 0-point correction. Typically for the 0-point correction, we'll just use density functional theory. But for the actual big barrier itself, if you were off by 10%, that might be way too much. So what you'll typically do then is try to do the most expensive, fanciest quantum calculation you can afford, the most precise you can, at the DFT geometry. So use DFT to find the saddle point. At that geometry, instead of believing the DFT energy, which might have errors of a few kcals per mole, you would instead run CCSDT, F12, biggest basis set you can afford at that particular energy to try to get the barrier as precise as you can, because you really care about accuracy of that number. So that's what we do. Here's a little story about the reaction past generations. I talked about that. Here's a little consistency check. If you assume that the TST formula is correct, this is the forward expression, this is the reverse expression, and so you can compute the equilibrium constant forward over reverse, and it turns out to be this, which is exactly the same thing you would get from the stat-mech thermo, using the fact that the Helmholtz free energy is negative RT log K, log Q. It just gives you this thing. So at least this formula, it might not be exactly right for the rate coefficients, but it's consistent, so it'll satisfy the thermo, which is a very important property. All right, time for a quiz. Okay, so let's consider the reaction of cyclohexadienyl radical. I'll show it to you. Okay, so this is this radical. This is the reactant. And it's breaking apart to make benzene I guess plus an H atom. All right, so this reaction, first of all, the running to the left is always running in a flame if you have any benzene. So you're running gasoline. Gasoline has benzene in it. You have some H atoms. You're definitely running this way. And this forward direction, you have sometimes there's other ways you can make this guy. And then this might be a way that you actually form benzene if you start with a fuel that has no benzene in it. And typically you run a flame with anything, and you measure the products. You'll typically see products with like 1% or 0.1% of the product will actually be benzene, no matter what you started with, because there are a bunch of channels that go this way. So this reaction is a pretty important reaction. So we want to know the K for this reaction. So the delta H of this reaction was already determined in 2009, 322 kilojoules per mole. The entropy of formation of this species was computed back in 1986, 375 joules per mole Kelvin at 550 K. So let's try to think of what we can do to estimate this reaction. So the first approximation is these two molecules look a lot alike. The only difference is that this guy lost an H atom. And H atoms, their frequencies of vibration are really high. So the mass of an H atom is very light, so therefore the K over M is big. So therefore the frequencies are big. So the frequencies are high. At moderate temperatures, if you have a high frequency, you don't get much Q from high frequencies, because the formula for how the partition function depends on the frequency, high frequencies are basically inactive. And that's because at normal temperatures, the high frequencies are not populated at all, so they're all V equals 0. So they don't really contribute anything to the Q. So first approximation is we can say that the Q for the transition state here might be approximately equal to the Q of the reactant. That'd be a reasonable first guess. So if we made that approximation, can we estimate what the K is? How would you do it? So what's the rate expression? What's the rate expression? So the transition state theory expression is what? It's something with this M and a bunch of sigmas. I don't remember how many sigmas, and maybe some kappa. There's a KT over H. There's a Q of the transition state over the Q of the reactant. Exponential negative delta E0. Is that all right? So what do we know? Well, these guys are a little confusing to figure out. We could probably do it if we spend a lot of time on it, but let's not worry about it. So these guys are factors like factors of 2, 6 maybe for benzene. Okay, so let's not worry about that one for a minute. Tunneling, that's way too subtle for us. We're not going to worry about that. K T over H, we can do these, right? We could look up what K is. We can look up, this is Boltzmann's constant. We can look up what the temperature, well, the temperature is specified in the problem, right? Was it 500 some Kelvin? Planck's constant, we know that. So these numbers we know. These numbers we could do, but I have to teach you about how you compute symmetry numbers. But these all turn out to be something that's less than a factor of 10. Okay? This is going to be something, we can calculate it. It could be pretty big, because Boltzmann's constant is a really tiny number, so it's the denominator, so this might be a really big number. This also has units. This is units per second. These guys are both dimensionless, they have the same units, right? So they're going to cancel out. And we just decided that we think that they might be similar. Is that right? So this might be about 1. So we need this number, and then we need an estimate of what the 0-point barrier height is going to be for this reaction. So how can we do that? Any ideas? No? So what does this potential surface look like? It's that we have a valley where we have the C6H7 species. And then it's going up, and there's a barrier, and there's a H plus benzene. Right? Yeah? So there's a barrier here. That's what we really want to know. This is E. And actually, really, what we want to know is the difference in the 0-point energies, right? So it's a little bit different, but about the same, okay, between these two. But in the problem statement up there, it doesn't really say anything about barriers, right? You see anything about barriers up there? No. So we really don't know with this. But a good way to think about it is that we're just breaking off an H atom, breaking off a bond, and it's disappearing. So that's an endothermic process to break a chemical bond. So most of this barrier is this energy difference here. This is the sort of the delta H of reaction. This is the big number. And then there's a little tiny number here because this energy of the barrier here is different than the energy of the product. You see that? So there's there's like a big term, which is this sort of endothermicity of the process, and then a little term for whatever the extra barrier is. And that extra little barrier is like the barrier for the reverse process. What's the barrier for an H atom adding on to benzene? Okay. So if we could figure out this number, then we would have at least a lower bound on what our barrier is. Does that make sense? So how can we figure that number? Do we have enough information? So in 2009, the delta H was determined. Is that right? So that number was known. This is equal to 322 kilojoules per mole, which is big, right? So as we said, this is a big number. Yeah?
So how do you know that the product side is getting so close to the transition state?
Yeah, I mean, how do I know this? I mean, this could be like this, right, instead? Is that what you're saying? How do I know? Yeah, I don't know. I mean, I know, because I'm like super world experienced chemist working in kinetics for however many, 30 years or something. So that's why I know. You guys probably have no idea, right? So it turns out that addition barriers of radicals attacking to double bonds have barriers that are like 5 kcals, 10 kcals, some handful of kcals. So this number here is something. I don't know how much it is really, but I'd be expected to be less than 10 kcals per mole, which is in kilojoules is less than 40 kilojoules per mole. But this one is 322. This is big. So for sure, this is bigger than this. I don't know if this is. It could be 40. It could be 38. It could be 22. It could be 47. I don't know. Something, right, in the range of 40s. If you wanted to really know it, how would you know? How would you do it? Yeah?
So I've seen a lot of times they say that your delta E is coming basically from your delta G.
Yep.
But I don't know under what conditions, well, it has to be some sort of equilibrium for that condition to satisfy, the actual jump to the other side. But
Yeah, the more exothermic a reaction is, typically the lower the barrier. Not always, but most of the time. So in this case, the reaction in this direction is very, very exothermic, 300 kilojoules exothermic. So if it's very, very, very exothermic, you'd expect the barrier to be very small. It's like there's a more driving force for this reaction. It really wants to go that way. It means it's smaller. Smaller than what, right? So I don't know. So in my experience, they're always less than 40. Exactly what it is, I don't know. If you wanted to know exactly, how would you do it? How would you compute it?
sometimes, you can choose your entropy and combine it with your delta H to get at the delta T and then relate the delta T.
You could, but then you need to know the correlation factor, which you don't know either, right? So, you need to know a number here, but to set a bound on the rate, you don't, right? So for sure, this barrier is bigger than 0, right? So this barrier height is between 0 and 40, 50, I don't know. So we have an error bar. Maybe the first thing to think of, you're going to have an error bar. This is a very important concept. Whatever you do, it's not going to be right. Okay? It's going to have an error bar. So don't be paralyzed by the fact that you can't get an exact answer. You guys are engineers, right? That's the whole field of engineering is about trying to roughly, yeah. That's engineering, right? If you were physics, no, it's not like that, right? Actually, physics is a lot like that too, but their image is not like that. In the engineering, that's what you're supposed to be like thinking. What is important? What's not important? So in this problem, what's important is that this is 320 kilojoules per mole. So this barrier is big. This rate's going to be small, right? It's going to be small because it's a gigantic EA. I mean, it's a gigantic delta H. It's got to have a gigantic EA because EA is going to be bigger, right? This distance here to the barrier top, which is either here or here, is definitely going to be bigger than this number, and this number is already gigantic. So that's the important thing. So in this expression, you have this number, which is going to be a big number because H is very tiny. So you have some big giant number here. This number is about 1, so our approximation. And so now the key thing is what's this number? And then you're going to plug in this number, whatever you put in. And this number, now we've just decided that delta E0 is going to be greater than 322. Right? And then I would tell you that it's also going to be less than 362 or something, because it's maybe 40 kilojoules higher. So somewhere in that region is what that value is going to be. So you're going to have a value in this range, 362 to 322. This is actually already a pretty tight error bar to tell you what the rate is. And so you plug it in, and you get your calculator out, and you just say, well, what's the rate going to be? All right? And then before you even do that, you say, well, what do I think the rate's going to be? And this number, I've done this one a lot because this shows up in every rate calculation in my life, KT over H. And this turns out to be like 10 to the 12th per second. So that's pretty fast. And so the whole thing's going to be about how gigantic is this, which is going to be pretty darn gigantic because KT here is like about 4 or 5, something like 4 kilojoules per mole at this temperature. And so this one's going to be greater than 300. So this ratio, this is going to be like exponential of negative 80, something like that, or maybe even bigger. So then you just have to calculate exponential of negative 80 compared to 10 to the 12th, and you'll see, is this rate going to be fast or slow? Is that all right? All right, let's stop and go get a photo.